So good evening, everyone. Last class we talked about pH metry. Today we will talk about pH metry, and that is one part of potentiometry. So we'll start with basic introduction to potentiometry, and then we will talk about pH, the measurement of pH, and the types of electrodes that we use. So now we'll start with the basic concepts of pH. So first we will define what is a pH. So by definition, a pH is defined as the negative log of the hydrogen ion activity, that is minus log of the H plus ion activity, and that is represented as A H plus, so which is called as the activity of the hydrogen ion. So this is the general definition or mathematical definition of pH. So here it is written as pH is equal to minus log of constant activity of hydrogen plus ions. So now when we take a dilute solution, the hydrogen ion activity, it is approximately equal to the concentration of the H plus ion. That is, the AH plus is approximately equal to the concentration of H plus for a very dilute solution. Now we know that the pure water is very lightly ionized. It is very poorly ionized, and at equilibrium we can write the ionic product of water as concentration of H plus into concentration of H minus, which is, we called it as the ionic product of water, and it is given as Kw. That is the ionic product of water, Kw. And we know that the value of ionic product of water is minus the 1 into 10 to the power minus 14 at 25 degrees centigrade. So from this we know that the concentration of H plus is equal to the concentration of OH minus, and that is 1 into 10 to the power minus 7. So when we take a log of both the sides, then we find that minus log of concentration of H plus minus log of is equal to concentration of OH minus, and that is what we call it as the minus log Kw. So from this equation we have a very important deduction, that is pH plus P of OH is equal to pKw. So here from the above these mathematical forms, we are very clear that the pH scale ranges from 0 to 14. So here we know that the pH of most water sources, since water is neutral, the most of the water sources, they lie in the range of 6.5 to 8.5. So a pH less than 7, that indicates it is acidic in nature, and a pH greater than 7, it indicates that it is alkaline in nature. So whenever for water we find that the pH is greater than 7, that might be due to the presence of some carbonates, bicarbonates, or of the sodium or calcium or magnesium, so which gives the slight alkalinity to the nature of the water. Then coming to the pH measurement. So for the pH measurement, it is usually done with a glass electrode and a pH meter. Nowadays we have digital pH meter. This digital pH meter, it measures using a glass electrode. So here the glass electrode, it is one of the most common examples of an ion selective indicator electrode. So when we write the overall cell reaction, that is when the glass electrode is taken as an with an external reference electrode, that is SCE, or that is the standard calomel electrode, then we can write it as, like the normal cell reaction, we can write it as the glass membrane. This is the single bar H plus, and the double bar here, it indicates the salt bridge, and the SCE here, it indicates the standard calomel electrode. Now to find out the cell potential, we can write, we have to assume that the standard calomel electrode is more positive than the glass electrode. So hence the the potential, the electrode potential now becomes, the total cell potential becomes E cell is equal to the potential of the standard gallium electrode plus the liquid junction, the potential of the liquid junction, and this is G0 minus 0.059 into log of H plus. This all comes from the Nernst equation. So then overall we can write it as E cell is equal to E star plus 0.059 log of H plus, where in terms of pH we can, since we know that minus of log of H plus is pH, so overall we can write it that the cell potential is equal to E star minus 0.059 into the pH. So here from equation 3.2 we have a very important inference, that is the cell potential is directly proportional to the pH of the solution. So here we have a term that is E star. So here E star, it is the combination of the SCE, that is the standard electrode potential of the glass electrode, the potential of the reference electrode, that is the SCE, and the liquid junction potential. So taking all these factor, we have clubbed those three terms and then it has been represented as E star. Now, besides these three potentials, there is also another potential which we call it as the asymmetry potential, which also contributes to this reaction. Now, what is this asymmetry potential? It is actually a small potential which exists across the membrane, even when the reference and the test solution are identical. So it develops inherently. So although the sources of asymmetric potential, they are not very much clear till today. However, it may be due to, because of the degree of hydration of the inner and outer surface of the glass membrane, or because of the design, its structural design, or it can also be attributed to the mechanical or chemical reaction when it is in use. So the degree of hydration of the outer surface will also change if the electrode is allowed to dry out for some time. So hence, that is why we always say that the electrode should not be stored in the uh, in the open. It should always be stored either in water or in the damp cotton wool. Now, since we do not know the value of the asymmetry potential, that is why we always need to calibrate the instrument, because to get our proper data, to get proper readings, we have to always calibrate the instruments. And since we know that this electrodes, they are very much sensitive to environment, so hence before performing any experiment, the calibration of the electrode is a must. Then now coming to glass membrane electrodes. So the pH glass electrode, it is very fragile in nature and it resists a variety of sample media with the exception of hydroxide. So this pH sensitive electrode, it forms the basis of many successful sensors for environmentally sensitive gases. So the glass membranes, they represent an important class of solid membrane ion selective electrodes. So hence we'll just talk about glass membrane electrodes. So here the glass electrode has been shown here in figure 3.1. In figure 3.1a, it is a typical glass electrode that consists of both an indicator glass electrode and a silver chloride reference. So here from this figure, we see that these electrodes, they have thin glass membrane that are fused to the end of the glass or a plastic body. Here they are fused at the end to a glass. The main body of the electrode, it contains an internal reference electrode, and that is mostly silver chloride, and it is filled with a solution that is usually, the internal solution is the HCl, 1 molar HCl. The selectivity coefficient of the glass membrane is such that the excellent dissemination against common cationic species is achieved. So this glass electrode is highly selective to cationic species because of the reference electrode and the internal solution that has been used here. And now here in figure 3.1b, we see an example of an ion exchange that occurs inside the glass electrode. So the pH electrode here It responds to hydrogen ions because of the result of the thin ion exchange sites that are present on the surface of the glass electrode. So the electrode, it consists of a thin layer, very thin layer of glass, and then that is almost 50 micrometer thick. That is 50 microns. That means 50 into 10 to the power minus 6 meters. So we see that the thickness of this glass electrode, of the glass that is present in the outer layer, is very small. Okay, so the charge is transported across the membrane by sodium or lithium ions that within the glass. The membranes are primarily, they are made of lithia, that is lithium oxide or sodium oxide, and silicon oxide, and some amount of alumina and boron oxide. And sometimes small multi-component glasses have also been used, whose sensitivity depends upon the type of the glass. So here, as shown in figure B, silicate glass has been used. That is, silicate is SiONA here, and the silica here, it reacts with the glass, and this electrode, when it is dipped in water, the sodium here that is present inside the glass electrode, it exchanges with the protons in water. So this, the surface of the glass electrode before hydration, that is SiONA. In the glass electrode we have H plus. So after it enters into the glass electrode, then we see it has now become SiO minus H plus, and sodium is, it comes out. So if the glass electrode, it is placed in a test solution, its glass membrane will have an inner and outer hydrated layers, and potential difference is developed due to the difference in hydrogen ion activities between the test solution and the outer glass surface, as well as the inner solution and the inner hydrated surface. Now this potential is very important, and this potential is called as boundary potential. The difference between the outside and the inside, when we have the solution, it is called as boundary potential. So, and this boundary potential is very much dependent on pH. So once the pH of the membrane of the solution is varied, then the boundary potential also varies. So now overall, the boundary potential is, can be called as the potential difference between the boundary potentials. So mathematically, when we can write the, for the boundary potential, we can write here H plus, that is GL indicated can see the overall boundary potential, that is EB. So EB, now it can be represented as E1 minus E2 is directly proportional to A1 minus AH minus of A2 minus AH. Now if we assume that the activities of the hydrogen ions in the inner and outer hydrated layer are same, then we can say that the boundary potential EB is directly proportional to A1 minus A2. But since the activity of hydrogen ions in the inner solution is constant, so this above equation, it reduces to EB is directly proportional to A1. Now we will apply the Nernst equation to this boundary potential, and then applying the Nernst equation, we find out that EB, that is the boundary potential, is equal to K1 plus 0.0591 of log A1, and then in terms of pH we can say that the boundary potential is equal to K1 minus 0.0591 into pH. So here K1 is the constant, which includes the constant factor of the hydrogen ion activity inside the solution A2, and here 0.051 log of A2 gives the pH of the hydrogen ion inside the solution. So this is how boundary potential is related to pH. So now we see the boundary potential is a measurement of the hydrogen ion activity or the pH of the external solution. So for measuring pH with glass electrode, the arrangement shown here in figure 3.2 here, this is a typical electrode system for measuring pH. Here they are commonly used. The arrangement has glass electrodes with silver chloride internal reference and external reference electrode, that is the saturated caramel electrode. So here in from figure 3.2 we see this is a typical electrode system that is used for measuring pH. So overall we can write it at this is the internal electrode, the H plus ion in the internal solution, the glass membrane, the H plus ion in the external solution, and the reference electrode. So this is how a pH electrode system is represented as. So now when we want to express the cell potential for this typical system, we can write it as E cell, that is the cell potential is equal to E of indicator electrode minus the potential of the standard Canomel electrode plus the potential of the liquid junction. So here it is a combination. So we can see it is a combination of three factors, that is the indicator electrode, the boundary potential, and the asymmetric potential. So here from substituting this equation, we have the boundary potential in terms of Nernst equation, and substituting all the values, we can write the cell potential is equal to E star minus 0.0591 into pH. So the E star here is taken as a constant, and it includes the potential of the reference electrode, the liquid junction potential, the asymmetry potential, the internal boundary potential, and it takes all the potentials into consideration. And since it is a constant, so it has been written as E star minus 0.0591 into pH. So this is how we can find out the E cell includes the boundary conditions and all others factors. Now, when we talk of this E star, since it includes the constant values of so many factors, so determination of this E star both experimentally and theoretically is very difficult. So therefore, calibration method is used to totally eliminate this factor. So what we do is, in this method, the first test solution is made of a standard buffer solution with the pH precisely known. So now we the standard pH buffers that are available in the market, buffer tablets, they come in pH 4, 7 and 9. So first buffer solution are made and we exactly know the pH of these buffers. Thus for the standard we can write it as E star minus 0.0592 into pH. This step is followed by measurement of the cell potential for unknown solution. So here the expression is given as pH U for the unknown solution. Then to eliminate this E star, we apply this equation, and this equation it has been adopted throughout the world and is called as a operational definition of pH. We know that the mathematical definition of pH is minus of log of concentration of H plus. However, when we operate with the instrument, and since so many other factors arises, so to eliminate the E star, the equation in 3.11 it is used throughout. So pH determination using glass electrode, it is most accurate and it is widely used. However, there are certain disadvantages associated with the use of this glass electrode. The first is the glass membrane is very fragile and it requires great care during the handling process. Also, the ordinary potentiometer, they cannot be used for measuring the potential of the glass electrode. Thus, since we cannot use ordinary potentiometers, we use electronic potentiometers, and with the use of such electronic potentiometers, standardization becomes an issue. So and also they cannot this potentiometers, they cannot be used in pure alcohol, acetic acid and gelatin. So that is why, since we have so many limitations, some of the common features that the glass electrode that can be used for pH measurement has been made. That is, it may be used in the presence of strong oxidizing and reducing solutions in viscous media. It can be used for solution having pH 2 to 10 with some special glass. The measurements beyond pH 10 can also be extended. It is should be simple to operate and immune to poisoning, and the equilibrium must be reached very quickly. So while measuring pH, we should be little careful because there are certain factors which limit the accuracy of pH measurements. Like some of these factors are what we the number one is a very important factor, and that is called as the alkaline error. So it has been noticed that the ordinary glass electrode, it becomes very sensitive to alkali and gives low reading in the very high pH range, that is in the alkaline range of above 9 or 10. So the reason for this error is that the glass membrane is very selective to hydrogen ion, but it also responds, or it is sensitive to other ions also. And this becomes more significant when the activity of the other ions is higher than the activity of the hydrogen ion. So here when we look into figure 3, it shows the deviation in pH measurement using a glass electrode under alkaline conditions. So here we can see as the pH is moved from 9 to 12, we see the deviation in different types of ions, Na plus, Li plus. So here it has been shown. So now here the figure, it shows the different the figure 3.3, it shows the different types of error that is produced by different cations taken in different concentrations. So here we see that the alkaline error is actually very much higher in case of sodium ion. Now why this is higher? It is higher because of the high selective coefficient of sodium ion. This is because sodium can reduce the use of Li2O glass in place of sodium Na2O glass. So this is why that is the alkaline error is maximum observed in the case of sodium ion. Now coming to the acid error. Similarly to alkaline error, we have another error that is called as the acid error, and it occurs in a very low region pH range, that is less than 0.05. So this zero point 0.5, sorry, this error is due to the activity of water which we have ignored during the representation of Nernst equation. So when water, we have always considered the activity of water to be one when it is taken in excess of the solution. However, when we have a very highly acidic solution, the activity of water, it becomes less than one, because most of the water is now used to hydrate the protons that are present in the solution. So similar effects has also been observed on addition of large amount of any salt or any non-aqueous ethan solvent such as ethanol. So the net result in this case is that the measured pH will be very high. That means it will be a very highly acidic solution. Then another error that has been some of the problems that has been associated. One is the alkaline error, another is the acid error, the third is the variation in junction potential. So what happens is, in most of the cases, the composition of the standard buffer solution and test solution are different. So in such a situation, the liquid junction potential becomes different. So as LJP becomes different, then the measurement of the pH also varies. Then the fourth point is error in the pH of the standard buffer. So now we know that we always first calibrate the instrument by using a standard buffer tablet. Now once there is a possibility that the buffer solution is not prepared with care, then the pH of the standard buffer will be different, so which will ultimately influence the pH of our readings. The fifth point that influences the pH is the temperature. So we know that a change in temperature is always very change in temperature always affects the pH measurements, because when temperature is increased, the activity of the ions that are present inside the liquid junctions, they also vary. So therefore, so when if there is a change in temperature during the measurement process, then we should expect error in the pH measurement. The another point that influences inaccuracy in pH is the calibration procedure. So once we have a problem with the calibration, if the calibration of the instrument is not done more accurately, then we have a problem during the pH measurement. Then there may be also certain errors which are related to the equipment, such as we can also face problems like power fluctuations or the parallax errors in the reading analogs and such cases. So these are the certain problems that can arise during pH measurement, so we should be extra cautious. Now coming to pH meter. So the instrument that required to perform potentiometric measurements, it first basically it includes a reference electrode, a indicator electrode, and a pH meter that we have already studied. So now ordinary laboratory voltmeters, they cannot be used for the measurement of the EMF because of the high electrical resistance of glass electrodes. So thus the pH meter is a voltmeter but with several critical additional functions. Not only does it measure the potential across the pH sensing and reference electrode, but also it converts the potential difference measurement at a given temperature into pH terms, and it provides mechanism to correct for the non-ideal behavior of the electrode systems. So modern electronic techniques, they allow the production of simplified pH meter that measures pH with an accuracy of almost plus 0.1 pH units. So since we are equipped with the microprocessors that are highly sensitive to the functioning of the electrode, and they display the temperature and the volt with which the pH meter is working. So now we'll just have some of the reference electrode and glass electrodes that we are using here. So first we'll begin with reference electrodes. The two most popular types of reference electrodes, one is the SCE, that is the saturated calomel electrode, and the other is the silver chloride, that is the AgCl electrode. So both these types of reference electrodes, they have many ideal characteristics. One of them is that they have fixed potential over time and temperature, and the potential does not change with time and temperature. They have long term stability, and they return to their initial potential after being subjected to small change in currents. So because of these three important characteristics, refer standard calomel electrode and AgCl electrode, they find much prominence in the types of reference electrode. So here the SCE, that is the standard calomel electrode, it is composed of metallic mercury, solid mercurous chloride, and a saturated solution of KCl that is in equilibrium with each other. So consequently, the potential of this SCE has been measured to be plus 0.2142 volts versus the standard hydrogen electrode that we know it has been taken as 1. So the SCE is more popular, and with a constant temperature bar, the error caused by fluctuating temperature can be eliminated. So here the SCE can be used as a reference electrode for a sample that does not exceed 80 degrees centigrade. Then comes the AgCl, the silver chloride electrode. It includes a silver wire that is coated on one end with an insoluble silver chloride salt. We know that silver chloride is insoluble, and the end is coated with AgCl. So when the electrode is immersed in saturated KCl solution, its potential at 25 degrees centigrade depends only on the Cl minus concentration, and it has been found to be plus 0.19 volt against the standard hydrogen electrode. So this silver chloride electrode, it should not be used in solution that contains species that which precipitates or which forms precipitate with silver. So this is one important point that we need to remember. The reference electrode should be prepared and maintained so that the level of the internal liquid that is present inside the electrode, it should be kept above the sample to avoid the infusion of the sample into the reference electrode. So this is one of the precautionary measures to avoid contamination by Cl minus or Ag2 plus or Ag plus ion. Then coming to measurement of pH. So now we have studied the different types of electrode. Now we will come to know, understand how the pH is measured using the pH electrode, the glass electrode. So the pH measurements, we know, the pH is a very important parameter for our day-to-day lives, because from the water we drink to the food we eat, plus to the to our uh, day-to-day diagnosis, we need to understand the pH. So pH can be measured in several ways. One of here, two processes have been discussed. One is the simple and is the use of a colorimetric indicator method, that is the use of pH paper, or we call it as pH strip. The second is the potentiometric method involving the pH meter, that is the glass electrode and pH meter. Now this spectroscope, this colorimetric method, it is not as popular, because with digitalized pH meter we can immediately know the pH of the solution. So this is why we are mostly, today we are as of today we are focusing on digital pH meter. So here we will start with the potentiometric method of the pH measurement. The pH is determined here by this method. The pH, it is determined by measurement of the cell EMF, which contains the indicator electrode immersed in the test solution, and the reference electrode, that is SCE, which remains contact with the test solution and the reference electrode via the LJP, that is the liquid junction. The EMF of this cell, it is measured with the pH, and the pH description we have already studied. So here, and the how to measure a pH has been, the process has been elaborated here. So the apparatus for the pH meter, it consists of the pH meter that contains the potentiometer, glass electrode, reference electrode, and a temperature compensating device. So to complete the balance, this circuit, the electrodes, when they are immersed in test solution, the potentiometer, it completes the circuit. Then the reference electrode. So here the reference electrode, it consists of a half cell that provides a standard SCE. They are mostly, or the silver chloride. The glass membrane electrode, several are available, but electrodes, even combination of glass electrodes are available at the market. Then beakers, we will take beaker to keep our test solution, and stirrer, the which we have a we can store our solution. Then we'll take the reagents. So first we will calibrate our instrument. So for this purpose, we have buffered tablets that are available with pH 4, 7, and 9. Because so first we will prepare pH buffer solution. For this process, 10.2 grams of anhydrous potassium biphthalate is boiled and it is cooled, and then it can be diluted to 100 ml. Then pH 7 buffer is prepared. To prepare pH 7 buffer, we will take 1.361 grams of anhydrous potassium dihydrogen phosphate and 1.4 grams of anhydrous disodium hydrogen phosphate, and then we will dilute it to 100 ml. So this measures the pH, gives the pH to be 7. Then for to prepare pH 9.2 buffer solution, we will dissolve borax in distilled water. So if we are not unable to prepare these buffer solutions, commercially available buffer tablets, they are available in the market, and then we can directly buy them and dilute it as per the instructions written in the manual. And then coming to the procedure. So generally what we do is, we, after the instrument is calibrated, then we can, here the figure 3.4, we can see a pH meter setup, and then we can say how to measure the instrument. So first we will keep the selector switch to 0 position, so which indicates we will adjust it to 0. Then before using the pH meter, we will remove the electrodes that are present inside the storage condition, and then we will wipe it with a tissue paper. Then third, we will mount the electrodes on the stand. For this, we will now supply power to the system. Then the temperature will be adjusted. A knob is provided. We will adjust the room temperature. Then we will, after that, we will take the standard buffer solution, and then we will immerse our electrode in the standard buffer solution. So we will then check the pH, and accordingly manually we will set the pH as per the standard buffer solution that we have taken. Then we will put the selector suit to suitable solution, and then in the pH range after we set it. Then again, after setting the instrument, we will take the selector switch back to zero position. We'll again wash the electrodes. So then we will set it with another buffer solution. Then we will wash the electrode and gently wipe it with a tissue paper. Now we will take our unknown solution. So after we'll take our unknown solution, the electrode we will dip into our solution, and then we will slightly shake our solution. So here, after the since the solution is stirred, we will leave it as such, and then the pH will be displayed on the screen. So then after our reading is done, we will take out our solution, we'll wash the electrode and gently wipe with a tissue paper. Now there are certain precautions that we need to follow while measuring the pH. First is, we will never touch the membrane of the glass electrode except tissue paper because it is very fragile in nature. The electrodes must not be removed from the solution unless the selector switch is at zero. We will never dip the glass electrode with a dehydrating solution. For sample analysis, there has to be equilibrium between the electrodes and the sample by stirring. First, we will stir it and then we will allow for equilibrium. If used for measuring pH of very albuminous substances, the glass electrode they must be cleaned properly because the albumin it sticks to the glass of the electrode. For basic solutions of pH more than 11, we cannot use the normal glass electrodes. We have to use glass electrodes of special composition. Then the glass electrodes may be covered in sleeve to save it from jerks, and the standard buffer of pH value should be very close to the possible pH value of the buffer. So commercially we can always take buffers of pH 4, 7 and 9.2. So these are the some of the precautions that we need to take while measurement of the pH. Then coming to pH titration. So pH titration, here they are similar to potentiometric titration. So the typical pH titration, basic acid base titration, they are performed using the pH, and that is called as pH titration. So here we will have a typical study about a typical acid base titration using pH metry. So now it is known that neutralization of acids and bases, they are always accompanied by change in the concentration of H plus and OH minus. So here in figure 3.5, this is a typical setup for a pH metric titration. So here what happens is, the one of the problems is the recognition point that is the end point or the equivalence point. So that is a very difficult to identify the equivalence point in pH titration. So what happens here is, in this titration, the base that is taken, it is added from the burette, and here is our solution. So that is why identification of equivalence is very difficult. So over the most of the titration range, the pH changes gradually, but becomes at the as the near point approaches, end point approaches, the pH changes very abruptly. So here, this is what we figure 3.6. We can say this is a pH titration curve. In x-axis, we have seen the volume of the titrant that is added from the burette, and in y-axis, we plot the pH. So here, so since from figure 3.6a, the calculation of the equivalence point becomes very difficult. So what we do, we plot a graph of dpH by dV, that is here shown in figure 3.6b. And from this figure 3.6b, we can see that the equivalence point can be calculated by this point. So this is how it becomes easier. Then also in figure 3.6c, we see that the second derivative has been used. Also the second derivative, they though although it is not very commonly used, but still the equivalence point can be known. In most of the cases, the first derivative is known, like more that 3.6a and b, they are plotted. So now coming to titration of a weak acid with a strong base. So here we will consider the titration of 25 ml of 0.05 molar acetic acid with 0.05 molar of sodium hydroxide. So this is a weak acid and a strong base. So during the starting point of the titration, the here we know that acetic acid is very weak acid in comparison to HCl. So because it dissociates very slowly, that is the degree of dissociation of HCl is very less in comparison to that of acetic acid is very less in comparison to HCl. So here the pH value, we can write the Ka as concentration of H plus into A minus by Ha, and then we have this equation, that is concentration of Ha is equal to root over of Ka, where Ka is called as the dissociation constant of the acid into C of acid, that is the concentration of the acid. So here the equivalence point of such type of titrations can be done when the titration is completed. Equivalent amount of quantities of acetic acid and sodium hydroxide will be present at the end point. So the titration salt, the flask or the conical flask, it will have a salt solution that is formed by a weak acid and a strong base. So here the H plus can be calculated as Kw into Ka by the C of salt. So this is where Ka is the dissociation constant of acid and this is ionic product of water. Overall, using this equation, so we can find out the pH of the solution. Then there will be certain intermediate points. So after determining the starting and ending points, we will consider the pH calculations for the intermediate points. So these points will correspond to the in presence of the ions in the solution and untitrated weak acid and salt that are present in the solution. So this will be given by this formula. H plus is equal to Ka into concentration of acid by concentration of the salt. So now here we will calculate the intermediate point, which corresponds to 5 ml of 0.5 molar NaOH when it is poured into the solution. So this is given by concentration of acid 0.05 into 20 by 30, which gives us this. Then after that, we will consider the concentration of the salt that is formed at this uh, point of titration, and we have added 5 ml of the solution. So therefore the Ka for acetic acid we know, and then substituting all this data we find that the pH is 4.14. So this is how, using such type of this calculations, we can find out the pH at the intermediate point. So after the equivalence point, that is after addition of 25 ml of NaOH, so both the excess NaOH and acetate, they give the OH minus to the solution, and thus the pH increases to further to alkaline. So here the titration curve can be categorized into three types. The of the titration of a weak acid with a strong alkali, it has three features. That is, the starting point of the titration is less acidic when a strong acid is being titrated. The weak equivalence point is weakly alkaline. The middle part of the titration is more slanting, and the titration is not very difference is not very great. So here in figure 3.7, you can see the pH titration curve when zero point 0.5 molar HCl is titrated with zero point 0.5 molar NaOH. See the we can see the change, and figure 3.57b, we can see how the change occurs when zero point 0.5 molar acetic acid is titrated with NaOH. Now this titration, this difference, it is because that H plus is a strong acid, and the concentration of H plus, it decreases when OH minus is available inside the solution. When we titrate a weak acid with a strong alkali, the H plus, they will not only combine with OH minus, but also they combine with the acetate ion. So as a result, the H plus decreases more rapidly at the beginning, and the titration curve bends down more sharply. So this is This effect, which smooths the titration curve, is called as the buffering action. So here it follows if the concentration of the acid is equal to the concentration of the salt solution, that is pH is equal to pK acid. So here it means that concentration of acid and concentration of salt have close values, then the pH will remain constant. Even if we keep on adding acid and alkali, the pH and pK acid, they will be remain the almost closer to each other. Then coming to modified glass and solid state membrane electrodes. Now we know glass electrodes, they can be made selective for ions other than hydrogen ion electrode. This modification is possible by changing the composition of the glass and the internal solution of the glass electrode. There is another type of glass electrode, that is lithium oxide, alumina, silicon oxide with, and also sodium electrode. So sodium electrode, it has been used in analysis of water analysis for the presence of sodium and biological fluids. So potassium or ammonium electrodes are also present. Then coming to solid state membrane electrodes. So in solid state membrane electrode, we use a doped single crystal membrane in place of a pure glass membrane. So these changes, they have been done to make these electrodes sensitive to different types of cations and anions. So here in figure 3.8, a solid state electrode, here it is given, this is a typical representation of a solid state electrode. Now coming to here the representation, this electrode system is similar to glass electrode system, and it contains an internal solution and internal reference. Here, for example, let us say the fluoride ion, its selective electrodes, it consists of lanthanum fluoride and an internal silver fluoride solution which is immersed in Kf or KCl. The lanthanum fluoride membrane, it is highly selective and it responds to fluoride ion. So here we can write the total representation of the lanthanum fluoride membrane in this way. And the potential for the electrode can be given as E cell is equal to E star minus 0.0591 log of activity of a fluoride minus. So where the E star, it includes the cell potential of AgCl electrode, the standard calomel electrode, the asymmetric potential and the liquid junction potential. So here the fluoride electrodes, so they have they are highly used in fluoride metal analysis, like if fluoride metals, their fluoride is present in water or in toothpastes or in bone, air. So this is used for detection of fluoride ions. So similar to fluoride ions, other solid state membrane electrodes have been used, like for example S2 sulfide. So here Ag2S has been used. Like for detection of cadmium, CDS Ag2S membrane has been used. So here table 3.1, it shows the different types of selective ions that can be measured or identified using different types of solid state electrodes. Now, based on the principle of ion selective electrodes, many gas sensing electrodes have also been developed. So these gas sensing electrodes, they can sense ammonia, carbon dioxide or nitrogen oxide uh, during measurement of air pollution. So this type of electrode, they have a gas permeable membrane and an internal buffer solution. The pH of the buffer solution changes the gas when it reacts with it. So here in table 3.2, different types of gas sensing electrodes have been listed. Like for ammonia, the internal electrolyte is ammonium chloride and it is ion selective electrode for pH. So here for sulfur dioxide, K2S2O5 is used, the internal electrolyte, and the membrane is made of silica rubber. So this is some examples of gas sensing electrodes. Now coming to applications of ion sensing electrodes. So ion sensitive electrodes, they are widely used in clinical diagnosis, for biological purposes, for design in pharmacy and also in analytical chemistry. So commercially available electrodes have been used for detecting H plus, fluoride, chloride, bromide, iodide, cadmium, cyanide, lead. sodium, potassium, and even and also for gases like ammonia, hydrogen sulfide, sulfur dioxide, nitrogen dioxide, etc. So pH measurements, the applications, some of the applications of pH measurements, they have been listed here. The pH metric method, they helps in detecting the end point of acid base titration. It is in pH metry is an important tool in studying the acid base equilibria. The estimation of alkalinity and acidity based on pH metry, it gives on the information on the buffering capacity of water. Even in wastewater treatment, the pH metry gives the amount of availability of different types of inorganic salts that are present in it. The industrial process control, especially in batch or flow through configurations, they are monitored through pH metry. In neutralization of wastewaters, to evaluate the doses of acid or alkali, we need pH metry, and pH metry has also been used for development of various types of biosensors. Further, there are other applications available for pH metry. So, in summary, we can say we discussed about the different in pH metry, the development of electrodes, the development of ion selective electrodes, and also the various applications of ion selective electrodes. So, with this, we finish the chapter on the first unit of today's class, that is pH metry. So, we'll take a short break and then again resume with the second unit. So now we'll start with the next unit, that is conductometry. In this unit, we'll talk about conductance, the various types of conductivity. Then we will talk about the measurement of electrolytic conductances and the applications of conductometry. So we'll start with a what basic introduction to electrolytic conductance. So now we know that the electrolytic solution, it contains free ions along with, in addition to other unidentified kinetically identifiable species. Now when we apply electric potential through this solution, macroscopically we see that there is a flow of current through the solution, and the chemical changes, they generally result in the liberation or dissolution of the electrode material at the point where the current enters or leaves the solution. Now this whole phenomena, we know it is termed as electrolysis. Now electrolysis part is called as the cell. The electrons are received from the negative end of the battery here, they by the negative electrode of the cells, they are then used up for the reduction reaction. So the number of electrons that is received at the negative end is given, the same is given to the positive end of the battery cell to form the oxidation reaction. So within the cell, the current is carried by the movement of ions, cations, that is the cations move towards the cathode and the anions, they move towards the anode. Now, this movement gives rise to the electrolytic conduction. So here, this electrolytic conduction, it depends on the mobility of ions and is affected by the inhibition that causes the resistance to the flow of these ions. Also, there are other factors like interionic attraction, solvation, viscosity, pH, which also influence the electrolytic conduction. So these factors, they also depend on the solute-solute, solute-solvent, and solvent-solvent interactions respectively. Then electrolytes and non-electrolytes we will define. So electrolytes, the compounds such as KCl, NaCl, these are the ionic compounds which furnish iron in solutions and they conduct electric current. They are electrolytes. There are also other covalent compounds such as HCl, CH3CO, which HCl, and acetic acid, which also form ions, they are also called as electrolytes. However, the all other substances that do not produce ions, they are called as non-electrolytes, such as carbon tetrachloride, benzene, they are non-electrolytes. Now sometimes electrolytes, they are also called as true electrolytes and potential electrolytes. So in true electrolytes, that is the cations and anions, they exist in their molten states, such as NaCl, that is in the form of Na plus and Cl minus. They are called as true electrolytes because they exist as Na plus and KCl in their molten state and also in their normal state. Plus, when NaCl is dissolved in water, it ionizes to Na plus and Cl minus and it conducts the current. The potential electrolytes, on the other hand, they do not conduct electricity in the pure normal state, but they conduct electricity when they are dissolved in water, like HCl, acetic acid. So when these are dissolved in water, they conduct electricity. That is why they are called as potential electrolytes. Then there is another classification. We call them strong and weak electrolytes. The electrolytes are called as strong electrolytes which ionize completely in the aqueous solution like NaCl, KCl. They are strong electrolytes. The weak electrolytes are those which ionize only up to a certain extent, such as acetic acid, HCN, they are weak electrolytes. Now, the behavior also electrolytes, it also depends on the nature of the solution. Like, for example, sodium chloride behaves as a strong electrolyte in water, but acetic acid, it behaves as a weak electrolyte in water. So when also on the other hand, when we take dissolved ammonia, both NaCl and acetic acid, they show similar type of dissociation. So that is why this strong and weak electrolyte, the term is they are very relative to each other. Then coming to conductance of the solutions. So here the ease of flow of electric current through a body is called as its conductance. So here in metallic conductors, the it is caused by the movement of the electrons. But in electrolytic solution, the conductance is caused by the movement of the ions of the electrolyte that is present in the solution. So the electrolyte conductance that is given as G, it is equal to the reciprocal of its resistance, that is G is equal to IR. So now we know that from Ohm's law, I, that is the current flowing through a conductor, is directly, when applied to E, is inversely proportional to R. So we know that from Ohm's law, I is equal to E by R. So combining these two equations, we get I is equal to EG. Now we know that the solution is a three-dimensional conductor. So the exact resistance, it will depend on the spacing and the area of the electrodes given by L and A. So the total resistance here can be this. The figure has been shown. So for this type of arrangement, the total resistance that is of the electrolyte that is present here in between the two electrodes can be given as R is directly proportional to L, that is to the spacing L. R is inversely proportional to area, that is 1 by A. So combining these two, we can say R is directly proportional to L by A. Now, if we introduce or remove the proportionality constant sign, then we will introduce a constant, and this the equation now changes to R is equal to rho into L by A. So here rho is the proportionality constant and it is called as resistivity. It was previously called as specific resistance, but now we call it as resistivity. That is, resistance is equal to resistivity into L by A. So now if we want to define this rho, so rho can be expressed as R into A by L. So that is, the rho is a characteristic property of a material and it is the resistance offered by a conductor of unit length and unit area of cross section. So here when we want to express rho in SI units, here the resistance is, we know it is expressed in omega. So therefore the unit of rho is omega meters, and formerly the resistivity measurements, it was made in terms of a centimeter, that is omega centimeter. However, we will, in today's terminology, the unit of resistivity or rho is given as ohm meter. Now we substitute the value of R in our Ohm's law, that is in equation 4.1. Then we get G, the conductance G is equal to kappa into A by L. So here kappa is the reciprocal of the specific resistance or resistivity, and it is called as specific conductance or conductivity. It is the reciprocal of kappa is the reciprocal of the resistivity, and it is called as conductivity. So therefore the unit of kappa will always be inverse or the reciprocal to that of resistivity, that is rho. So hence the unit is ohm inverse meter inverse. However, in SI system, the unit for conductance is called as Siemens and it is given as the capital S. So, the unit of conductivity here, it is written as Siemen into meter inverse, where 1 Siemen is equal to 1 omega inverse. So, we should always remember that 1 Siemens meter inverse is equal to 1 by 100 Siemens centimeter inverse. But in practical applications, when we use a conductivity meter, so here the unit comes in the form of millisiemens per meter or microsiemens per meter. Now coming to cell constant. So for a particular cell, when A and L are constant, the quantity L by A, here it is called as the cell constant K. That is K cell is equal to L by A. Now when we substitute this value in the equation of G, we get kappa is equal to G into cell constant. So that is conductivity can be defined as the observed conductance into cell constant. So to obtain the how we should obtain the value of cell constant, now it is always not necessary to first to determine L and A. So we can also measure it by another process, that is it is measured by a solution of known conductivity. That is mostly KCl solutions are used because their conductance have been measured with high precision. So a given solution of KCl of conductivity kappa dash, it is placed in the cell and its resistance R dash is measured. So the cell constant will be equal to kappa dash R dash. So of the case for the KCl solution. Now we know that conductance is an additive property. So that is why the total conductance can be given as the summation of Gi plus G. So now here the G of water, it is negligible in comparison to summation of Gi, and thus the total G can be written as sigma of Gi. Sigma the summation of Gi. Then coming to molar conductivity. So in order to understand compare the conductivities of different electrolytes, there is a quantity that has been introduced and it is called as molar conductivity. We represent this molar conductivity in lambda m. So it is related to kappa by the relation lambda m is equal to K by C. The molar conductivity is usually expressed here in units Siemens meter square per mole or Siemens centimeter square per mole. Now here the C that is expressed in this equation is of the unit moles per dm cube. So then for to make the conversion easier, we have another term that is called as equivalent conductivity. So which is given as lambda EQ is equal to 1000 into kappa by C. However, we mostly also call it as lambda EQ has been also called as molar conductivity. Now coming to variation of conductance with concentration. The conductivity of an ion, we know it increases with the increasing concentration. For strong electrolytes, the increase in conductivity with increase of concentration is very sharp. But when we consider a weak electrolyte, the increase in conductivity is very gradual. So in both the cases, there is an increase in conductivity and that occurs due to the increase in number of moles of ion per volume of the solution. Now for strong electrolytes which are completely ionized, the increase in conductivity is almost proportional to its concentration. But when we take weak electrolytes, the increase in specific conductance is not very large because of very poor ionization of the electrolyte. So here in table 4.1, the molar conductivity of certain electrolytes in aqueous solution, it has been shown here. For KCl, NaCl, HCl, those are strong electrolytes, and acetic acid, sodium acetate, which are weak electrolytes, the value have been shown here. So it is observed that in contrast to the conductivity, the molar conductivity, that is lambda m, here from this table, the lambda m, it increases with decreasing concentration for both weak and strong electrolytes. Now, if we plot the molar conductivities of a large number of electrodes against the square root of the concentration, we see that they fall into two types of categories. So, one is the strong electrolytes where there is a small increase in molar conductivity, but then there are the weak electrolytes where we see a very high change in molar conductivity with dilution. So here the typical from figure 4.2, we took the plots. From the plots we see lambda m versus the concentration. Here we see this is for acetic acid and here this is for KCl. For KCl the drop is very instant, whereas here the drop is gradual for the acetic acid. So the conductance of a solution, it depends on the number of ions and the speed with which the ions move in solution. In case of strong electrolytes, the number of ions is same at all dilutions, because we know that strong electrolytes, they are almost completely ionized, and the variation of equivalent conductance with dilution is due to the change in the speed of the ions. But when we take a concentrated solution of such electrolytes, the interionic attractions among the oppositely charged ions would be quite appreciable. Now, the ions may also form some ion pairs of the type A plus B minus that would not contribute to the conductance. So, here at infinite dilution, when the ions are far apart, the interionic attractions are almost absent, and thus this point at infinite dilution, that is denoted by lambda infinity. So hence, it may be concluded that in the case of weak electrolytes, the increase in molar conductivity with dilution is mainly because due to the increase in number of ions in the solution and the small interionic attractions at very higher dilutions. So with this, there comes a new term that is called as the limiting molar conductivity. So here, this limiting molar conductivity is obtained by extrapolating the curve from C to 0 for strong electrolyte. And when we observe this, here Conrad's law found out this relation, that is lambda m is equal to lambda infinity minus b root c. So here b is the constant for a particular electrolyte, and lambda infinity, it indicates the molar conductivity at infinite dilution. Now, how can we obtain this lambda infinite? So here, to obtain lambda infinite, we extrapolate the curve c tends to 0 and the intercept, so that we get the value of lambda infinity. And this cannot be used for measurement. This process cannot be used for weak electrolytes. This measurement process is only applicable for strong electrolytes. So here we know by applying, there is, by applying here at the law of infinite dilution, we can see that lambda infinite is equal to lambda infinite of the cation and lambda infinite of the anion. That is the ionic conductivity at infinite dilution of the cation and anion. So the molar conductivity of the ionic species, it is a measure of the amount of current carried by ions in question. So comparison of the molar conductivities is therefore more meaningful when we compare their charges here or in terms of their equivalent conductivities. So here in table 4.2, the limiting ionic molar conductivities and the limiting ionic equivalent conductivities of certain ions at 25 degrees, they have been listed here in table 4.2. So now coming to ionic mobilities and transport number. So we have always seen a difference in the values of limiting molar conductivities of similarly charged ions. So why this difference arises can be explained in the mobility of different types of ions in solution. So we know the mobility of an ion in solution is very much dependent on the size of the hydrated ion. So thus, that is, the ionic mobility is defined as the velocity with which an ion would move under a potential gradient of 1 volt per meter in a solution. So for instance, ionic mobility U is related to lambda infinity by the following equation, that is lambda infinity of cation is equal to Z plus U plus F, and also it is equal to Z minus U minus F, where Z plus and Z minus are the valencies of the cation and anion. U plus and U minus represent the ionic mobility, and F is the Faraday constant. So if all the values is known, then lambda infinity can be calculated. Now, to find the values of lambda infinity, there is also another constant quantity that has been defined. It is called as transport number or transference number, and it is written as T plus for the transport number of a cation and T minus for the transport number of a anion. So mathematically, it has been defined as T plus is equal to lambda infinity by lambda m, and T minus is equal to lambda infinity by lambda m. Thus, the transport number and the limiting molar conductivities, they are measurable quantities. The limiting molar conductivities of certain ions, it has been shown here in figure table 4.3. These values are very important. Once the molar ionic conductivity value is obtained, then using this 4-point equation 3, we can calculate the lambda m. Then here in table 4.3, the limiting ionic mobilities has in water for some cations and anions have been listed here. Now, when we look at table 4.2 here in this case, then we see that Li plus ion has a larger hydration cell. It has a lower mobility than K plus ion. Similar argument can also be applied for F minus and Br minus ion. But very exceptional mobilities they are observed for OH plus or for H plus and OH minus. This is because the case the charge here is transported through proton jump mechanism along with other migration mechanism. Like here, if we see into H plus, so here there is a proton jump which helps in the transport number. So here in this case, the hydrogen ion jumps from O1 to O2, followed from O2 to O3. So this is called as the proton jump mechanism. So, however, this conduction mechanism has been particularly observed for water and only in hydrogen bonded solvents. Then effect of other factors on conductivity. So first is the effect of temperature and pressure. The conductivity of all electrolytes, it increases with increasing in temperature. So the variation of molar conductivity at infinite dilution with temperature is given by this formula, that is in equation 4.15. So where the lambda infinity at T and lambda infinity at 25, it indicates the molar conductivities at T degrees centigrade and 25 degrees centigrade, and X is the constant for each of the electrolyte. So here we see the conductivity increases with increase in temperature, and the conductivity increases slightly with increase in pressure. So why there is an increase in conductivity with increase in pressure? This effect is mainly through the changes that occur in the viscosity of the medium, which decrease by an increase in pressure. And then coming to the effect of solvent. So in solvents of low dielectric constants having small ionizing effect on the electrolytes, the electrostatic forces between oppositely charged ions would be appreciable and the equivalence conductance will have small value. So therefore the solvents with high dielectric constants, they yield more conducting solutions. Then coming to the viscosity of the medium. The dependence of conductance on viscosity of the medium is given by Walden's rule. So according to Walden's rule, the equivalent conductance of an electrolyte is inversely proportional to the viscosity of the medium. That is lambda infinity into eta is equal to constant. So this is what follows from the Walden rules. Then coming to measurement of electrolytic conductance. The conductance of a solution can be measured by measuring the resistance offered by the solution that contained within the two electrodes. So for measuring the resistance, a Wheatstone bridge is employed. Therefore, we need to understand what is this Wheatstone bridge. So here a simple Wheatstone bridge it has been shown in figure 4.3. It is employed to measure the resistance. So it works on the principle of obtaining balance between two arms with the help of a balance indicator, that is a galvanometer at the condition of potential being equal. That is, here let us assume that Rx here is the unknown resistor. There are two other standard resistors, R1 and R2, but the R3 that is present here, it is adjustable in nature. The whole bridge is connected to a power source S, and the battery and a tapping key here it is placed. The key is placed for the controlling the connections. Now to measure the resistance Rx, so the bridge is balanced by adjusting R3. So in total, so the potential here at B will always have to be equal to the potential here at point D. That is, EB is equal to ED, or I1 R1 is equal to I2 R2. Similarly, IR3 is equal to I2 Rx. So dividing all the equations, the resistance of the unknown resistor is, that is Rx, is given as R2 by R3 into R1. So once we know the values of R1, R2, R3, the Rx value can be find out, and once all are known, the conductance is, we know it is the reciprocal of resistance, and it can be given as R1 by R2, R3. So this is a very important finding or the application of the Wheatstone bridge. Alternatively, we can also find out by incorporating an amplifier into the above circuit. Here it is shown in this figure. Now in the Wheatstone bridge, we had four resistors. Here we will incorporate an amplifier. So the current from the input potential is balanced by the current from the amplifier output. That is, E0 is equal to EI into Rf by Rx plus 1. So with respect to the conductance, the above equation is changed to this. So then thus when we have an amplifier, we can use this equation to calculate the conductance. Then coming to measurement of conductance of a solution. The principle of Wheatstone bridge, it can be used to measure the conductance of solutions. However, the following considerations must also be kept in mind. So these are the certain features that we need to keep in mind. So now since a direct current, it polarizes the electrodes in the conductivity cell by electrolyzing the solution. To avoid polarizing, an AC source of power must be used in place of a DC source. Usually AC voltage of 3 to 6 volt with frequency 50 or hertz or 1000 hertz can be used across points A and C. The second point is, a suitable conductivity cell is located between the points C and D. Thus, here the Rx represents the resistance of the conductivity cell. Now, since the cell also acts like a small capacitor, and to balance its effective resistance, capacitive resistance, a variable capacitor must also be inserted into the bridge. The balance indicator may be an AC galvanometer, but other devices may be used, such as an earphone can act as a balance indicator if the frequency of the AC source is in audio range. A magic eye, which gives a green fluorescence as a result of electrons striking a phosphor coating inside the glass, has also been used. For precise measurements, a cathode ray oscilloscope is used as the balance indicator. So these are the some cases where different balance indicators can be used. Here in figure 4.5, it shows a conductivity bridge circuit. Then conductance can be read directly on commercially available instruments. Now several digital instruments are also available, which gives us very easy measurements in a very short time span. Then coming to conductometer. So we know that conductance is equal to reciprocal of resistance, and it can be measured by from the Wheatstone bridge. So the inverse of resistance gives the conductance, and it can be directly measured using an instrument called as your conductometer. So a special type of conductometer, it consists of an AC source, a Wheatstone bridge, a null detector, or DC display, and a conductivity cell. Now, to avoid the side effects of polarization, that is the change of the composition during the measurement, AC is mostly preferred. The instrument has an arrangement to cover the supply of 50 Hz to 1000 Hz. Now, when we want to measure low conductance, then lower frequency is preferred. Several inexpensive conductometers, they are commercially available. The instruments, they come as a line operated unit with and without digital readout. Figure 4.6 gives the view of a, here it shows a typical conductometer which can be operated with given instructions. Then coming to cells. Various types of cells have been designed and they are in use of the measurement of the conductance. They are mostly made of Pyrex glass fitted with electrodes of platinum or gold. So to overcome the imperfections, and they are coated, also coated with a finely divided platinum black. This is achieved. How can we prepare platinum black? We can electrolyze a 3% solution of chloroplatinic acid which contains lead acetate. So for highly conducting solution, the electrodes are widely spaced, whereas for low conducting solutions, the electrodes are mounted near each other. So a cell suitable for conductometric titration, here it has been shown in figure 7ABC, the typical cells that are used for conductometric titrations. So for most purposes, a special cell is not required and good results they are obtained by clamping a commercially available dip cell. Here it is a dip cell. Here in figure 7.4b, we see a dip cell. So that is dipped inside the beaker which is placed on the magnetic stirrer. So with this arrangement, the dipping cell, it should be lifted clear of the solution after each addition from the burette to ensure that the liquid between the electrodes, they are properly mixed. Now, since the absolute conductivity values which are not required, so it is not necessary to know the cell constant. Now, for spot checking, a dip type conductivity cell is used. So here in certain titrations, open beaker is used. However, when we have uh, dilute solutions, an open beaker might not be used because atmospheric carbon dioxide may interfere and affect the conductance values. Now the process for measuring conductance is, first we have to plug the instrument to an AC supply. Then we will put the frequency selector switch to the required frequency. Then the mode should be set on cal, that means to calibrate it, and it will be set you by using the knob. Then the conductivity cell electrodes we will be connected to the terminals of the instrument. Then we will take the standard KCl solution. We will introduce a stirring rod and put the solution on the beaker in a magnetic stirrer. Then we will insert the conductivity cell in the solution. After that we will see that the electrodes are completely in a, they are dipped in the solution and they do not touch the side of the beaker. Then we will switch on the instrument and warm it up for 2 to 5 minutes. So then we will measure the conductance of the standard KCl solution uh, by switching the knob to read position. So after we have measured the conductance of the KCl solution, we will now measure the, we will remove the KCl, we will wash the conductivity cell with distilled water, and then we will take our unknown solution. So then we will again same perform the same type of experiment. Then we will calculate the cell constant from the given equation, that is K cell, the cell constant is equal to conductivity by observed conductance of the standard. Then we will calculate the conductivity of the unknown solution, that is the cell constant into the observed conductance. Then for titration work, the value of the cell constant is not required. When we want to perform a titration, that is conductometric titration, then the cell constant is not required because the cell constant, it remains unchanged during the titration process. Now, when the range selector is switched to a new position, it is essential to check the calibration again. So, we will set the meter again to read 1 with the sensitivity control, that is if any deviation is observed. Now, the conductivity cell, when it is not in use, it should be kept in distilled water to prevent the drying of the platinum electrodes. This is a very important part. The electrodes should always be kept in distilled water, or sometimes they are dipped in KCl solution, because once they are removed and kept dry outside, then the platinum electrodes, they become dry, and there is possibility that the electrodes will be damaged. Now in case of fouling, the conductivity cell electrode plates, we clean them by keeping in dilute potassium chromate solution containing sulfuric acid, that is what we call it as chromic acid solution, for 24 hours, and then it is washed with running water for the, or mostly it is washed with distilled water. So distilled water is a good choice to remove the, for washing the electrodes. Now coming to applications of conductometry. So the high sensitivity of the conductometric measurements, it makes it an important tool for environmental analysis and other applications. A continuous or spot check measurement of the conductance, it is employed usually with a dip electrode cell and meter. In certain cases, continuous reading of the conductance is also employed. Since conductance measurements, it depends on the ionic concentrations, the purity of the steam distillate or the demineralized water, and the ionic contents of the water, they can be checked with measuring conductance directly. Now various metal industries, electroplating baths and rinse baths, they are monitored by such conductometric methods. The most common application of direct coulometry has been for of direct conductometry has been for estimating the purity of distilled water. Now this was first discovered by Kohlrats. Kohlrats, he worked with 42 successive distillations of water, and he obtained a conductivity of the water with specific conductance kappa is equal to 4.3 into 10 to the power minus 8 Siemens per centimeter at 18 degrees centigrade. So traces of any impurity, if that is present in the water, it will increase the conductivity value. Ordinary distilled water in equilibrium with the carbon dioxide of the air, it has a conductivity of about 7 into 10 to the power minus 7 Siemens per centimeter. The seawater, it has much higher value of conductivity, and the conductometric measurements, they are widely used to check the salinity of water in oceanography. This is one of the greatest applications of conductometry. Now, measuring the conductance of soil, it helps in finding the moisture contents of soils at various places with potable instruments. So now we know all soil, they contain different amount of water soluble salts that make up to 0.1% of the total value or more. So these salts, they might be present in the form of sulfate, chloride, carbonate or bicarbonate of different metals such as sodium, potassium, calcium or magnesium, and thus because of the presence of these salts, the conductance of the soil becomes measurable. So accordingly, the soils have been classified as saline and non-saline depending on the nature and quality of these soils present. So once we measure the conductivity of a saturated extract with water of saline soil, then it has been found at 20 degrees centigrade, the saline soil has a conductivity of greater than 4 millisiemens per centimeter inverse. So now we see that the nature of the soil, whether it is acidic, alkalinity, they can also be known from the conductometric measurements. Now based upon the relative change in the conductance or resistance of the solution with the addition of an electrolyte, various methods, they have been developed for the titration of a strong acid with a strong base, weak acid with a weak base or a strong base, and a mixture of strong acid and weak acid versus a strong base. So other type of titrations which can be performed conductometrically, it include displacement titrations, like for example a salt of a weak acid, that is sodium acetate, versus a strong acid like HCl, or a salt of a weak base, that is ammonium chloride versus NaOH. There are also precipitation titrations, that is silver nitrate versus KCl. There is also complexometric titrations like mercury nitrate versus KCN or EDTA, versus metallic ions, and there are also oxidation reduction titrations like the titration of ferrous iron versus potassium permanganate. So these are some of the titrations, conductometric titrations that we come across in analytical chemistry. Then conductometric titrations based upon precipitation or complex formation, they are not very much useful as those that involve the neutralization reactions. So the conductance changes during these titrations are not very large. During the precipitation reaction and complexometric titration, the conductance values do not change very largely as those observed with acid base reactions, because no other reagent it approaches the ionic conductance of either H plus ion or OH minus ion. So the main advantage to the conductometric endpoint is its applicability to a very dilute systems and to system that involve relatively incomplete reactions. Like for example, when neither a potentiometric nor indicator method can be used for the neutralization titration of phenol, then conductometric titration can be successfully applied for this neutralization titration of phenol. So direct measurement of conductivity is potentially a very sensitive procedure for the determination of various parameters like the degree of dissociation of a weak electrolyte and its dissociation constant, ionic product of water, solubility and solubility product, and hydrolysis constant of the acid salt. So in summary, in this unit, we have talked about various parameters like resistance, conductance, resistivity rho, conductivity kappa, equivalent conductance lambda equivalent, and molar conductivity lambda n, and molar conductivity at infinite solution, that is lambda infinity. So we have also talked about cell constant, the relationship between various parameters, and the various important applications of conductometry. So here with this we finished the unit on conductometry. So next class we'll again start with a new unit. This much for today. Thank you.
Hello, hello.